Hello, and welcome back to our studies in physics. We already in a previous video learned how to graphically add two vectors. And recall that the graphical addition of two vectors is not exact. It gives you kind of a ballpark. Tells you that the resultant vector should be either longer or shorter than one or both of the vectors involved in the addition, and generally what direction it points. So in this video, what we're going to do is talk about the exact addition of two vectors. So if we want to know exactly what we get when we add two vectors together, we need to use the following method. So recall that a vector can be graphically represented as an arrow that has some length. So there's vector A. And I have another vector, let's say this is vector B. So here are the two vectors that I want to add together, and let's say I know their exact magnitudes and directions. For example, placing a coordinate system on the end of vector A allows me to say that this vector has a certain length and makes a certain angle with respect to the horizontal. Notice I needed to give two pieces of information to fully define A. I need to say start at an origin, of which I need to define where that's going to be located, and at an angle of theta, go out some particular length, if we're talking about displacement, and that will tell you the displacement of the object, so a magnitude and a direction. But notice that I could also give that information about vector A using a different way of describing it to you. I could tell you to start at some origin of which we have agreed on, and I could tell you how far to walk out along the x-axis, and then I'd say now turn and now walk this far along the y-axis, and that would also describe vector A to you. So that gives you two different ways that you can actually transfer information about a vector quantity and fully define it. So one is called the magnitude and direction form. Okay, so we're just going to henceforward call this MAD, magnitude and direction. So this simply says vector A is some length, which I'll just use the scalar A without an arrow, that's the length of it, and it makes an angle of theta degrees. So you know, if this is a displacement, that could be 15 meters at an angle of, oh, that looks like maybe, 48 degrees, 50 degrees, something like that. Quadrant 1, obviously, and right around 45 degrees. Okay? What about vector B? Well, we could do exactly the same thing. Again, we just put a coordinate system on the tail of vector B, and notice that vector B only lies along the x-axis. So we could talk about the magnitude and direction form of vector B. Magnitude and direction form of vector B would be it has some length B. And what angle does it make with respect to the coordinate system? Well, that's the angle right there. And we'll just put a prime on that theta to distinguish it from this theta. So this is going to be at theta prime degrees. Again, notice that B doesn't get a negative sign, okay? It's just some magnitude at some angle, and in this case that would be the 180 degrees, right? So here theta prime is going to be equal to 180 degrees. Okay? So this is the magnitude and direction form of expressing a vector. Another form for expressing a vector is called the component form. Okay, so how do we express vector A in component form? Well, in component form, we use the directions of the coordinate system that we have defined to express the information about the vector. So as I was saying earlier, I could also tell you how far to go along the x-axis and then how far to go along the y-axis, and that is the information that is given in component form. So vector A is going to be equal to some distance ax along the x-axis, and it's the positive x-axis, right? I mean, it's in the positive direction along the x-axis. Plus, because we also need this leg of the journey to get to the tip of vector A, plus some distance ay along the, in this case, plus y axis or direction. Okay, so this is a lot of stuff to write, and it's going to be convenient to define what are called unit vectors to keep track of the 4 different ways that we could move with respect to the origin. We could go along plus x, we could go negative x, we could go plus y, and negative y. In component form, you're always traveling along the direction of one of your coordinate axes. You must be traveling along that direction. So notice that I would travel some distance along x and then some distance along y, and that also would tell you about my displacement that I experienced in vector A. Okay, so what we want to do then is define unit vectors. Unit vectors have length 1, and they have no units associated with them. So this means that when I use unit vectors, they don't change the magnitude part of any quantity that I'm looking at. So what are the unit vectors we're going to be using? Well, we're going to be using x hat minus x hat. When we put hats, that means it's a vector, but it has a length of 1 and it doesn't have any units associated with it, right? Direction doesn't have any units. Okay, y and minus y. So in 2 dimensions, which is what we're going to be limited to in this class, we aren't really going to be worrying about the 3rd dimension, even though we know spatially there are 3 dimensions, but at the level we're studying physics, we're only going to be worrying about 2 dimensions. Then these are the only 4 directions that I would be able to tell you to go to get to the tip of vector A in a component form fashion. So if x and y were instead north and east, right, so this is east and north, I could tell you how far to go east and then how far to go north. You could think about this also as a geographical coordinate system, or we could talk about horizontal and vertical. It's just going to depend on the problem that we actually use as to, you know, what these real directions would translate to for in the problem. So x hat is going to keep track of the words along positive x direction. Negative x hat's going to be along negative x direction. And likewise, y hat and minus y hat, positive y hat is along positive y direction. And negative y hat is along negative y direction. So there are the 4 unit vectors that we'll be using in this class. Now notice that I can tighten this up now so that I can express vector A as ax, and that's going to be along the positive x direction, so that's x hat plus some distance ay, and that's going to be along the positive y direction. Now notice that ax and ay are the lengths of the sides of what happens to be a right triangle. So let's pull this down here, and here is vector A, and notice that this distance right here is the ax x hat. So it has a length and a direction. And then ay hat is going to be that piece right there. So that's x hat and that's ay y hat. So the lengths of the sides, the magnitude parts of AX and AY, can be found using trigonometric functions if we know the length vector A and this angle theta. So notice that with this particular right triangle, theta being defined here instead of over here, then I can write down that the length of AX is going to be the hypotenuse A times the cosine of the angle theta. Notice that's the adjacent side, adjacent Harkin's cosine. AY is going to be equal to the hypotenuse A times the sine, it's the opposite side, that Harkin's sine of the angle theta. So we can find the exact lengths of the sides of these triangles, or the distances we would need to move along the x and y axes by using the trig functions. In addition, notice that if I had instead just the component form of the vector, so somebody tells me this is how far along x and this is how far along y, I can transfer that information to magnitude and direction form by using Pythagorean's theorem, squaring this side, adding them together, taking the square root would tell me how long the hypotenuse is. And if I know both of these sides and I wanted this angle, I could use the tangent function in trig, or specifically inverse tangent over the ratio of these two sides to give me the angle. So this trig function is super important in getting back and forth between magnitude and direction form and component form, or MAD form and component form. Now, what are the advantages of one over the other? Oh, and let's go ahead and just finish B in component form. Notice that I could write vector B then as just some length B along the negative x direction. So that now is the component form of vector B. So they're both described there. The component form happens to be the only form that we can add vectors in. So it'll be quite common that we'll be getting information about vectors in magnitude and direction form, or MAD form, and we'll want to add some vectors together. But in order to do that, we have to stop and we have to move the vector from the MAD form to the component form so that we can add then those vectors together. So you can only add in component form, only add vectors in component form. So if I wanted to add vectors A and vectors B to get some resultant vector, vector A plus vector B, then I would take vector A, which is some length AX along the x direction. This is in component form. I must be in component form, plus some vector AY along the y direction. And now I want to add vector B, so plus, and here's my vector B, some magnitude along the minus x direction. Now we add x's to x's and y's to y's. Notice what we've done. We've taken our vectors and we've projected them into pieces along the x-axis and pieces along the y-axis. So back when we were in one dimension and we were adding two displacements, we just used pluses and minuses to keep track of the directionality part of the vector. And here we are doing something similar. We're transferring that information to something that's a little bit more complicated, but still using the same principles. So we're taking vectors, and by putting them in component form, we're finding how much of them, or the projection of them, that is along each of the axes, and then we're just adding up pieces along that particular line using pluses and minuses. So notice that along the x-axis I have a piece AX, and that's along the positive x direction, and then I have a piece along the negative x direction as well. So these pieces will get added together with proper signs, and there is no piece of B along the y-axis, so we'll just have one contribution along the y-axis, and that'll be from vector A. So now my resultant vector then can be written as AX minus the length B along the x-axis. And whether this is going to translate to being along the negative x direction or the positive x direction is going to depend on which is larger, ax or b. If b is larger, then this is going to be a negative sign. And if ax is larger, then that will be a positive sign. So this, then, is the addition of two vectors in exact form. We'll see you next time.